Yeah, fine. So, good evening to all of you. Good evening to all of you. My voice is audible? My voice is audible?
Yes, sir.
Yes, sir.
Yes, thank you. Fine. Fine. In yesterday's class, we are going to discuss about learning of simple linear regression model using stochastic gradient descent optimization technique. So today we are going to discuss about the batch gradient descent optimization or batch gradient descent optimizer. So we are going to discuss about batch gradient descent optimizer, and we are going to discuss about how gradient batch gradient descent optimizer will help the simple linear regression model to learn some information or to update its model parameter based on the available data. Fine. So yesterday it will take 2 hours, but today is not like that, because we are not discussing about the simple linear regression model again, and also from here all the optimizers which are based on the gradient descent optimization technique, there is a slight modification, only with the slight modifications. Fine. Yeah. Yes. Fine. So now we will discuss about how batch gradient descent optimization technique or optimizer will help to train simple linear regression model. And the simple linear regression model will be, so yesterday we discussed. So if you consider this is a simple linear regression model which will predict some output y, based on the input using the two model parameters called m and c. Based on two model parameters m and c. So yip equal to m into xip plus c. So this is the simple linear regression model. So the simple linear regression model will be helpful to predict some information or to predict some data based on only one single input variable. So let us assume I want to develop a simple linear regression model, and I want to train a simple linear regression model based on some input data xia and yia. So these are I represent the sample. So first sample, second sample, third sample, fourth sample, like that. Now I want to make simple linear regression model to learn some information from the previous data or historical data which is available in the form of the data set. So data set contains the information or data which is used to train the simple linear regression model. That means, suppose if you want to build a simple linear regression model to predict a load at particular hour of the day based on the load at the same hour of the day, but same hour but in the previous day, then you have to prepare a data like this. So the first column will represent the previous load data and the second column represent the next load data, next day load data. Like that you have to prepare your data set. Similarly, the data set will be changes based on which problem you want to use this simple linear regression model. Simple linear regression model. The application to application, problem to problem, data set will be changes. Data set will be changes. Suppose if you want to build a simple linear regression model to help a utility to participate in energy market to successfully trade energy. So if the utility if utility or retailer wants to purchase or sell energy through energy market, you have to place a proper bid. You have to place a proper bid in terms of the market price. So for that you have to predict the market price. Suppose if your strategy is prediction of the market price at a particular hour of the day based on the market price available in the previous day, then you can go with the simple linear regression model. Then data set will be changes. Then the data set will contain the market price information. The data set contains the market price information. In the first example, the data set contains the load information. So the data set will be changes with respect to your problem. With respect to your problem. Suppose if you are working on wind forecasting. Okay. So suppose if your approach is forecasting the wind speed at particular hour of the day based on the available wind speed in the previous day, then your data contains the wind speed information. Your data set contains the wind speed, previous day's wind speed and next day's wind speed. Like that the data will be available. But the simple linear regression model will be same. It will not change. It contains the M and C parameter. That's it. But how the M and C parameters will be updated based on that is depending upon the what data is we are given and which type of algorithm you are using. The model will not change. That means our brain will not change. We make our brain to learn something based on first time maybe we learn Telugu alphabets like that. Maybe later we will train our brain to learn English alphabets A, B, C, D. Later we will train our brain to learn numbers, right? Like that the data will be changes, but your brain will not change, like machine learning model, right? So your data may change, that is depending upon the problem. Your optimizer may change based on the like school. If the school kid is change from one school to another school, that means the strategy will changes. Like that your learning algorithm strategy also changes. Fine. So now we are going to discuss about how our batch gradient descent algorithm will work, will make simple linear regression model, will learn and update M and C model parameters based on the available data. It is almost everything is similar to the, as I said, the optimizer to optimizer, there is a very small variation. Right? So it is batch gradient descent optimization technique almost similar to your stochastic gradient descent optimization technique. Almost similar. Then where is the change? We will discuss now. But now we will start with step 1. So step 1 is related to the initialization. So you have to read your data set XIA and YIA. You have to read eta, learning rate 0.01, let us assume, and you have to initialize number of epochs. Let us assume 100. And what else? Anything I forgot? Anything I have to initialize?
decent variables.
Yes, thank you. So we have to initialize, because in gradient descent optimization, initial values must be randomly initialized, randomly assigned, right? So what are the model parameters for a simple linear regression model? The model parameters are so I'm assigning m equal to 1 and c equal to -1. So but you have to observe your m value and c value. Generally we have to generate or assign randomly by using the random function in Python, or by using the rand, a function called rand in MATLAB, right? Fine. So that's all. So initialization part is over. Now step 2. What the step 2 is? So in the step 2 we have to set iteration count, set iter equal to 1. You have to set iter equal to 1. Now in step 3 what we will do, we'll explain now. It will change. So please concentrate. Very minor change. You can also tell the you can also yourself, you can develop the algorithm also. In batch gradient descent optimization and stochastic gradient descent optimization, almost both are similar. In main, only the difference is in stochastic gradient descent optimization technique, we will take a sample by sample and we will update the model parameters. Try to remember, in stochastic gradient descent optimization, we took one sample, we will update the model parameter, and later we will take second sample, later we will update the model parameter, later we will take the third sample, we will update the model parameter. Like that, we are taking the sample by sample, and we are updating the model parameter by taking the each sample. So that is in case of the stochastic gradient descent optimization. Whereas in batch gradient descent optimization, we are not taking the sample one by one. We are taking all the samples at a time. And we are calculating the mean square error over all the samples. Later we will update the model parameters. Someone, can you keep in mute? Can someone keep in mute? Fine, thank you. Fine. So I want to repeat again. In stochastic gradient descent optimization technique, we will take sample by sample, first sample, and we will update the model parameter. Second sample, we will update the model parameter. Third sample, we will update the model parameter. So sample by sample we are doing, right? But whereas in case of batch gradient descent optimization, we will take all the samples available in the data set as a batch at a time. We take all the samples available in the data set, training data set, as one batch, and we will feed all the samples at a time, and we are calculating the total mean square error, and later we will update the model parameter. Not sample by sample. We will take all samples at a time, and later we will update the model parameter. Whereas in case of the stochastic gradient descent optimization, we will take one sample at a time, update the parameter, second sample, later update the parameter. Like that we are proceeding in case of the stochastic gradient descent optimization. But whereas in case of the batch gradient descent optimization, we will consider all the samples in the data set as a single batch, and we will feed all the samples to the network at a time. Later we will update the model parameters. Now suppose what I am telling, if you understand, then you can easily give the answer for me. Let's assume I want to run the training algorithm to train the simple linear regression model for 100 iterations, using batch gradient descent optimization technique, whereas the number of samples available in the data set equal to number of samples ns. Number of samples available in the data set equal to 1000. Now my question is, how many number of updates will be happened for each model parameter, our complete training algorithm? 100, right? It is 100 because for first iteration we are taking all the samples at a time, we will update the model parameter, and second iteration we will take all the samples at a time, we will update the model parameter. So how many number of samples are there? It is irrespective of the number of samples. It is depending upon the number of iterations. For one iteration, one time your model parameters will be updated. Your model parameters will be updated. Thank you. Fine. Yeah. Fine. So now, yeah. So now I told that in batch gradient descent optimization technique, we are considering all the samples. That let us assume the number of samples available in the data set equal to number of samples available in the data set equal to ns. Number of samples available in the data set equal to ns. And generally, what is our objective function in the learning algorithm of simple linear regression model? What is our objective function? Our objective function is minimization of mean square error, that's equal to 1 by n sigma I equal to 1 to n and yi minus yip whole square, right? So that can be written as the objective function is of mean square error, that's equal to 1 by n sigma I equal to 1 to n yia minus yip means it is a mxia minus c whole square. Fine. So in case of the stochastic gradient descent optimization algorithm, we are taking n equal to 1. Trying to recollect. So in case of the stochastic gradient descent optimization algorithm, we are considered n equal to 1. Because we are taking the one sample at a time and we are calculating the error, and based on the error we are updating our model parameters m and c. Right? Now, if we consider batch gradient descent optimization algorithm to train a simple linear regression model using the dataset containing the ns number of samples, then what will be the modification that we have to make in the of mean square error? What modification we have to do in the of mean square error in case of the batch gradient descent optimization? Anyone please? What may be the modification we have to incorporate in objective function that is called of mean square error? Can someone, I think given in the chart. Yes, perfect. We use this. Srinath, good. So it is the ns, right? Because in case of the simple linear regression model, the number of samples we have considered is one sample at a time. We are calculating the error. That's why n equal to 1. But here we are taking all the samples at a time and we are calculating the error, and based on the error we are updating our model parameters. As we are considering all the samples in a training dataset at a time, so definitely this will be equal to ns, not n equal to 1, it is a ns. We are taking all the samples at a time. So your mean square error will be like this. Your objective function will be like this. Fine? Perfect. So this is your objective function, or this is your loss function, or this is the cost function. Now what we have to do in step 3 in case of the batch gradient descent optimization. In step 3 for stochastic gradient optimization, in step 3 we are assigning a sample equal to 1. But what you are expecting, what we are doing in step 3, ఇందులో ఏం చేయొచ్చు, step 3 లో ఏం చేస్తాము? It's okay, fine, I will tell. So
we initialize a sample.
Not required, madam. Here sample is not, initialization is not required, because in stochastic gradient descent optimization we are calculating the error for each sample. That's how we are taking the sample equal to 1, and later we are calculating the error, later we are calculating the updating the model parameter, later we are making the increment for the sample count. But here we are passing all the samples at a time. So you can directly calculate the gradients. Here we are calculating the gradients directly. So in the step 3 we have to calculate the gradients directly. It's called objective function, f, or cost function. So your gradients are two gradients, that is a dou f by dou m and dou f by dou c. The number of gradients is depending upon the number of model parameters. So what will be the dou f by dou m now? So it is the f. So what will be the dou f by dou m? So your dou f by dou m value equal to 1 by ns sigma I equal to 1 to ns and differentiation of this term. And half mean square error, right? Half mean square error means 1 by 2. So here is 1 by 2. Right? So what happened? So once we are differentiating this one, these two come to forward and this 2 and 2 will be cancelled. So we have only yia minus m into xia minus c. And what else I have missed here? That is I am differentiating with respect to m. So I have to add minus xia. I am adding xia here and keeping the minus n outside. Alright. So only new thing coming here is 1 by ns into sigma I equal to 1 to ns, because we are feeding all the samples at a time. We are feeding all the samples at a time. Right. So now, so similarly in case of dou f by dou c, that is the gradient of a loss function or cost function with respect to the modular parameter c, then we have what we have, there is a 1 by, we have to differentiate with respect to c, then 2 will become forward, 2 will be cancelled, then we have 1 by ns sigma I equal to 1 to ns yia minus m into xia minus c. And what else I have to add? Coefficient for c, there is a minus 1, so that minus come into here. So that what we have to do in case of batch gradient descent optimization in step 3. So what we are expecting in step 4? What we are expecting in step 4? So in the next step we have to do what we have to do in the next step. So we have to update our model parameters. So once you are calculating the gradients, you have to update your model parameters. So that's model parameter m equal to same equation, m equal to m minus eta into dou f by dou m. So same equation, but similar equation, same as the stochastic gradient descent optimization, but the value of the dou f by dou m value will be different comparing to the stochastic gradient descent optimization. In case of the stochastic gradient descent optimization, dou f by dou m value equal to this only, dou f by dou c equal to this only. But in case of the batch gradient descent optimization, this complete whole term come into the picture. So you have to update your model parameters. You have to update your model parameters, m equal to m minus 8 into dou f by dou m, and c equal to c minus eta into dou f by dou c. Fine. Step 4. That is the step 4. So now we are updating the model parameters. So once you are updating the model parameters, you are going to next step. That is step 5. In the step 5, what we have to do is, so once the model parameter updation is over, what we have to do? So we have to increase your iteration count. You have to increase your iteration count. That is the iter equal to iter plus 1. That means you have to increase the iteration count. Right? So now move to the step 6. So forget about this one. Now go to the step 6. So that is, you have to check for the iteration count whether it is reaching to the maximum or not. That is the convergence criteria. So if iter count is less than or equal to number of epochs what you defined, if it is satisfied true, then we have to go to which step? Else we have to go to next one. That means, else means this condition is false. This condition is false means your iteration count is greater than the number of epochs what you defined here. So then you have to go to the next step. The next step is step 7. So that means we are coming to the step 7 means you are reaching the maximum number of iterations. So your algorithm will stop. So once your algorithm will stop, you have to take the m and c values, latest m and c values, and you have to calculate error matrices like MSC, RMSC and MAE on both training and testing data set. And yesterday some maybe Sai Babu or Srinath asked if we calculate the MSC, what is the need of RMSC and MAE? Definitely, I agree with you. So I told that as a practicer, so you have to calculate MSC, RMS and MAE, and any of these three, not three, sometimes we can use a mean absolute percentage error. So this is also another error matrix. You can use any of these four to compare your model performance, or to justify your model performance, or to compare your model performance with other models which are available in the literature. So these error matrices will help us how accurate our model is, and also which help us to compare our work with respect to some existing models available in the literature. So these are the metrics we are generally using, right? So this is the step-by-step procedure for updating the model parameters by using the batch gradient descent optimization technique, right?
So which one is the best one, sir, out of these?
Not best one, it will give the just numerical value, madam. It will give numerical value. So suppose, for
No, out
example,
of these four, sir, out of the four things which you gave, which is the best one? We can't find it out.
if you think I can't say which is the best one, because suppose I am comparing the model 1 and model 2. So suppose if you compare
We have to
MSC,
compare and
suppose
okay.
if your model is a model 1, let us assume you are using some forecasting application using the simple linear regression model. Let us assume simple linear regression, some other model, and you are calculating the MSC. Then you have to compare the MSC value of the model with which you want to compare. So if MSC value of this one is less when compared to this one, definitely your RMSC value also less when compared to the RMS value of this model, because it is just square root of this one. So you can use any of these parameters. You can use any of these parameters. For example, suppose as a research point of view, I am telling, suppose the paper which you are referring for your research work, and they are mentioned the RMSE value and MAE value of their models, then you have to do RMSE value and MAE values for your model also to compare, to validate with other models. So that's why I am telling you have to work on all these parameters, and you can use which based on your flexibility, your requirements. So this is a step-by-step procedure to calculate, to update the model parameters of simple linear regression model, which in the batch gradient descent optimization technique, right? So now here one thing is missing. So there is a go-to. If iter count is less than the number of epochs, that means you are not reaching the maximum number of epochs, then you have to go to which step? We have to go to which step?
Step 3.
Step 3. Yes.
Step 4.
No, it is the step 3, madam. It is the step 3, because once one iteration completed, again go to step 3 and you have to calculate the gradients. Step 4 will come into picture. If you go to step 4, we require these gradients. That gradients will be coming from here. So if the number of epochs not reaches your maximum count, then you have to go to the step 3 and you have to calculate the gradients, and later you have to update model parameter. And this process will be repeated until you reaches the maximum number of epochs. So fine, I hope you understand the procedure. Only change is what is your change in the objective function. So based on the change in the objective function, your gradients are changes, and these equations remain same, similar to your simple linear regression model, so stochastic gradient descent optimization. But only thing is the dou f by dou m value and dou f by dou c value will be changes because of the change in your objective function. Fine. So now we are going to discuss about some numerical calculations for simple linear regression model training by using the batch gradient descent optimization method. So let's assume a data set, input is xia and output is yia, actual values. So it is a 0.2 and 3.4 and 0.4 and 3.6, like that. Let us, I am taking the only data set having the 2 samples, because we are doing the hand calculations. We are doing the hand calculations, right? Now I want to use this data. I want to train a simple linear regression model based on this available data set by using the batch gradient descent optimization technique. So step 1 is you have to read your data set xia and yia, and you have to read your learning rate eta equal to 0.01, and you have to set number of epochs. So I am setting 2. I am setting the number of epochs equal to 2, and you have to randomly initialize your model parameters. That's equal to m equal to 1 and c equal to minus 1. So it is randomly generated. So I am giving m equal to 1 and c equal to minus 1 for our calculation purpose. But when you are writing the code, then you have to choose randomly generate the values for m and c. Now in step 2, so you have to set iteration count iter equal to 1. Now in step 3, we are going to calculate the gradients. So what is the gradient? That is dou f by dou m with respect to the m, that's equal to minus 1 divided by, what is the denominator here? What is the denominator? That is the ns, right? That is the ns. Sigma I equal to 1 to ns into yia minus m into xia minus c into xia. Trying to, just now I have derived in the previous whiteboard. Right? So what is the value of ns? What is the value of ns here for us? So the value of ns for us here is minus 2. ns equal to 2, because we have the two samples, the sample 1 and the sample 2. So here we have the only two samples, so ns equal to 2, that is the minus 1 by 2. Sigma I equal to 1 to 2 into yia minus m into xia minus c into xia. Right? So that's equal to minus 1 by 2, that's a 0.5. Now I equal to 1. I equal to 1 is first sample. So what will be here? First sample, for the first sample. When I equal to 1 for the first sample, what will be here? yia, that is the 3.4 minus m, that's equal to 1, xia, that's equal to 0.2, minus c minus 1, that's the plus 1, into xia, that's equal to 0.2. So that is for I equal to 1 for the first sample. Next, I equal to 2, because it is a sigma term, so it is a plus. Now what will be? Anyone can tell what will be here? What will be here? Next, what I have to write?
3.6.
Yeah, 3.6
minus 1 into 0.4
plus 1
into
into
0.4.
good, thank you.
0.4.
Thank you, good. So that's it. So this is the dou f by dou m value. So you can compute what is the value. If you want later, you can compute. It is 1 by 2 into. So if someone have a calculator, or try, if you give some value, then it's better for me. So 3.4 plus 1, 4.4, 4.4 minus 0.2, 4.4 minus 0.2, that is a 4.2 here, right? It is a 4.2, 4.2 into 0.2, that's a 0.84, I think. 4.2 into 0.2, so that is a 0.84, plus here 3.6 plus 1, 4.6 minus 0.4, 4.6 minus 0.4 means 4.2, 4.2 into 0.4, 4.2 into 0.4, 428, 4416, maybe I think it's a 1.62. So please check it once if I was wrong. So minus 1 by 2, so sum of these one will be maybe 2.46, so that's equal to minus 1.23. Maybe this is a minus 1.23. Fine. So this is a minus 1.4 to the dou f by dou m value. Similarly, you have to calculate dou f by dou c. So your dou f by dou c value equal to emustunamma. So for dou f by dou c, our function will be minus 1 by ns into sigma I equal to 1 to ns yia minus m into xia minus c. That this will not come into picture, right? So that's equal to minus 1 by 2 sigma I equal to 1 to 2 and yia minus m into xia minus c. So that's equal to minus 1 by 2. So it is similar to this portion only, except multiplied with 0.2. It's similar to this one only, except multiplied with 0.4. So definitely maybe this value is sum of these two, 3.4 minus 1 into 0.2 plus 1, that is 4.2, and it is a 3.6 plus 1 4.6 minus 0.4, that is the that is the plus 4.2. So finally we have the minus 4.2, that is the dou f by dou c, dou f by dou c. Right? I hope you understand how I am calculating the gradients based on the available data set. So once we are calculating the gradient, so we have to go to the step 4 where we are updating our model parameter. So we are updating our model parameter m equal to m, that means what is the value of m? I will write here m minus eta into dou f by dou m. So what is the value of m here? That is the previous value, that is called initial value here. 1 minus eta 0.01, eta 0.01 into dou f by dou m, that's equal to minus 1.23, minus 1.23, right? So what is the value will be? Minus into minus plus, so 1 plus, so this will be the 0.0123, so we can call it as 1.0123, 1.0123. That's the new m value. Previous value is 1, now the new m value is 1.0123. And similarly, what is the value of c? So c equal to c minus eta into dou f by dou c. So that's equal to, what is the c value? Minus 1 minus eta 0.01 and dou f by dou c value minus 4.2. So what it will be? Minus 1 minus into minus plus into 4.2 into 0.01, that's equal to 0.042. So maybe this value is 0.958, right?
Eight.
Eight.
Yeah, so c equal to minus 0.958. So it's the new c value and this is the new m value. So now our step 4 also completed. Once the step 4 is completed, so you have to remember these two values, 1.0123 and it is a minus 0.0958. So I am taking 1.01 minus 0.96. So step 4 is completed. So in step 5 what we have to do, right? In step 5 what we have to do, we have to update our iteration count. Iter equal to iter plus 1, that's it, right? So iter plus 1, that's equal to 1 plus 1, that's equal to 2. Whereas in step 6, I think in step 6 we are checking for the convergence criteria, that is if iter is less than or equal to number of epochs or not. So what it will be? Iter is equal to 2, less than or equal to number of epochs we are defined in the initial step, that's equal to 2. So 2 less than or equal to 2, so it is satisfied. Then we have to go to step 3. 3 means we have to calculate the gradients. We have to again calculate the gradients, right? We have to go to the step 3 again. We have to calculate the gradients again, right? So if you go to, okay, otherwise I will write again. So step 3 we have to calculate the gradients again. Then and here the data set is 0.2 and 3.4 and 0.4 and 3.6. So it is the x and this is the y data set. So step 3, again go to step 3. So dou f by dou m, that's equal to minus 1 by s into sigma I equal to 1 to ns, and here yia minus m into xia minus c into xia. So that's equal to, here we are taking the two samples 1 and 2. So this will be 1 minus 1 by 2 sigma I equal to 1 to 2 yia minus m into xia minus c into xia. So that's equal to minus 1 by 2. So when I equal to 1, that is the first sample. So 3.4 minus, what is the value of m? What is the value of m we have to consider here?
1.01.
Yes, it is a 1.01 into xia, that is a 0.2 minus c. So what is the c value you have to consider?
Minus 0.9.
958. So that is I am taking just 0.96. So 958, 96. So this is for I equal to 1 into 0.2 plus we have to go I equal to 2 now, second sample. So then we have to take same 3.6 minus 1.01 into x value 0.4 plus C value 0.96 into 0.4. So like that you have to calculate the dou F by dou M, and similarly you have to calculate the dou F by dou C. So dou F by dou C value equal to same fashion, but only this will not come into picture in case of the dou F by dou C. This XIA value will not come into the picture. So it will not come into picture, and this 0.4 also not to come into the picture. Just addition of this term and divided by 2 multiplied with -1. So that is the dou F by dou C value. So you have to calculate the dou F by dou C value also. So once you are calculating the dou F by dou M and dou F by dou C, so let us some value we are getting dou F by dou C. So once these values are coming, then we have to go to step 4, where we have to update our model parameters. M equal to m minus eta into dou F by dou M. So that m equal to, what is the value here? M, is it 1? Here m 1, 0.01.
1.01.
Yes, it is the 1.01. And minus 0.01 into dou F by dou M. Dou F by dou M will be coming from this equation. Dou F by dou M will be coming from here overall. So that value you have to keep here and update the M value. Similarly, you have to update the C. C equal to C minus eta, that's equal to 0.01 into dou F by dou C value. The dou F by dou C value coming from here. Like that we are updating them. Here C equal to minus 0.958 minus 0.01 into dou F by dou C. Right? So this is the updation of the model parameters during the second iteration. Once the updation is over, then we are going to step 5. You have to update your step 5 here. So you have to update your iteration count. So iteration count is, previous iteration is 2, now it's a 2 plus 1, that's equal to 3. And step 6, you have to check for the iteration convergence. So current iteration equal to 3 now. Less than or equal to number of epochs what would define in the first step, that's equal to 2. So it's a false case. It is a false case. So if it is a false case, we have to go to the 7th step, where we have to read in step 7, we have to read latest M and C values, final updated model parameters of the simple linear regression model, that is the M and C, right? M and C, and based on these M and C values, you have to calculate the mean square error and remaining all error matrices. So this is the step-by-step procedure for batch gradient descent optimization. How that in this fashion, the batch gradient descent optimization technique will update the model parameters of the simple linear regression model. So these are numerical calculations, and also explain the step-by-step procedure. So so you can adopt the same concept to the multiple linear regression models also. So see, in the simple linear regression model, you have output y, m into one input x plus c. That means you have one input and one output. So that's why you have the only two model parameters, because one input and one output. But in case of the multiple linear regression model, you have to find a linear equation. You have to find a linear equation, or you have to represent output value in terms of the multiple input variables in the linear relation. So then y equal to, let us assume you have the input features x1, x2, x3. Let us assume you have the input features x1, x2, x3. Based on these three input features, you are going to predict y, right? So then your mathematical modeling of multiple linear regression model will be like this: y equal to m1 into x1 and m2 into x2 plus m3 into x3 plus c. Just I am giving some information. You can try it later, but you can do the same understanding to the multiple linear regression model also, right? So I hope you understand. That means, so now in the previous case, your simple linear regression model will be like this. So simple linear regression model will be like this. This is the M, it is the X, and we are addition, we are passing the C, and it will give the output Y. Whereas in case of the multiple linear regression model, what it's doing is multiple linear regression model will be like this. So let's assume I want to build a multiple linear regression model to predict an output Y based on the three input features x1, x2, x3. Then your model will be like this. It is the x1, and this is the x2, and this is the x3, right? So here it is the m1, and it is the m2, and it is the m3. So you have to sum it all, and you have to add bias term or constant term C. So it will going to predict the Y. So this is the multiple linear regression model, and this is the simple linear regression model. So you can observe the complexity of the model will be changes. The complexity of the model will be changes, right? So you can adapt the what we discussed till now about the simple linear regression model using the stochastic gradient optimization or batch gradient optimization. You can adapt same thing to the your multiple linear regression model also. Just I am giving just a brief introduction about some brief mathematical modeling about the multiple linear regression model. I think you are understanding, but I'm not going with the step by step procedure for this one also. You can try yourself, right? So now, if I think you are understand this concept, so now my question is, if anyone able to, please respond. I want to build a multiple linear regression model to predict load at a particular hour of the day, to predict load at particular hour of the day, to predict load at a particular hour of the day based on load at previous hour and also load at same hour but the previous day. That means what I want to convey with you is, now time is 7:50. Yeah, I want to predict the load at 8 p.m. based on load available at 7 p.m. that means 1 hour before, and also load available at the 8 p.m. yesterday. So your application is load forecasting. You want to forecast the load on some substation or some utility. Okay, now your approach is, that is the problem is load forecasting, and your approach is, I'm not telling this is the best approach, I am telling just an example. Now your approach is, you are going to predict the load at particular hour, that means 8 o'clock load based on the load available at the 7 p.m. today and 8 p.m. yesterday. So that is your approach. If that is your approach, so definitely you have one output to predict and two inputs, right? One input is load at 7 p.m. Another input is load at 8 p.m. yesterday. So two inputs. You want one output, what you want to predict is load at 8 p.m. today, right? So if this is the approach for you, as we have the two input features and only one output variable, so you can't go with the simple linear regression model. So you have to go with the multiple linear regression model. So if you go with the multiple linear regression model, now my question is, how many number of model parameters are there for this problem? How many number of model parameters are there? How many number of model parameters we need to update for this problem?
3.
Yeah, good.
3, sir.
It is 3. Because we have the two inputs, so you have to predict the load at L of t, that is you have to predict the load at particular hour, particular time, based on load at previous hour t minus 1 plus load at yesterday, that means 24 hours before t minus 4. So this is the one variable and this is another input variable. Now into m1 plus it is a m2 plus bias term c. So you have the total 3 model parameters m1, m2 and m3. Sorry, c. So you have the 3 model parameters. if this is the problem and if that is the approach. So the complexity of the model will be changes based on your approach, right? So if your approach is very complex, then definitely your model also becomes complex. You will have the more number of model parameters. But if your approach is very simple, very narrow, then definitely your model will be very simple model, very narrow model, right? So problem is same. Some people may predict in this direction, and some people may include weather conditions at that time, and also they have also considered whether that is a weekend or a week off. So some other parameters also they may consider. Finally, ultimate goal is you have to produce an accurate model which can predict the load properly. So why I am giving this example is just to give some brief about the multiple linear regression model, but I'm not, you can do yourself also if you understand what I discussed in the previous case, simple linear regression model using the batch gradient descent optimization. You can do the similar case you can apply for the multiple linear regression model also. So if you have interest, you can also try. So if you have any doubt, definitely I will help you if you call me, if it is required for you. But whereas as part of this course, we are only focusing on the simple linear regression model, but with various type of optimization algorithms. Fine. Now my second question is, and next question is, let's assume for the same problem, for the same approach, I am using stochastic gradient descent method. I am using stochastic gradient descent method having 100 iterations and 100 samples, 100 iterations and 100 samples, right? Then how many updates will be happened over a complete algorithm, not for one model parameter, total updations by considering our complete model. So I'm getting some, yeah, fine. So my question is please someone mute, I'm getting some disturbance. Yeah, my question is, I want to use the stochastic gradient descent optimization to train this multiple linear regression model for this problem, and my algorithm has 100 iterations and my dataset has 100 samples. My question is, how many updates will be done, not for one parameter. I am asking how many updates will be done during the complete iterative algorithm. How many updates will be done over a complete iterative algorithm, not per parameter, complete. Understood? I think understood, right? Yeah. So what may be the answer? What may be the answer? There it is. How many? So actually, yeah, you said one person said it is a 10,000. Perfect. One time. But I am asking not for one model parameter. For M1, for M2, for C. There is an updation for M1, there is an updation for M2, and there is an updation for C. So my question is, I am asking just for understanding purpose only, just how much you are understand to know those things. I am asking. If I am asking
30,000, sir.
Yes, there is a 30,000. If I am asking total number of updations per one parameter, then it will be 10,000. I am asking total number of updations over a model over complete iteration. So it is a total 30,000 because it is a number of model parameters into number of iterations into number of samples, right? If I ask the same question in case of the batch gradient descent optimization, then how many number of updates will be happened over complete model, for complete model, not total number of updations per parameter. I am asking total number of updates over a model.
300.
Yes, it is a 300. So because in case of the BGD, total number of observations are your model parameter multiplied with number of iterations. that's equal to model parameters are 3 into 100, that's equal to 300. Just I'm discussing all those things only for your understanding purpose, how you are getting the information, how we are how much my information what I shared is reached with you. So fine, yeah, it's for my that theory part is completed. Now we are going to discuss about the some lab discussion. So and I will discuss about tomorrow we are going to discuss about the mini batch gradient descent optimization. So after mini batch gradient descent optimization, we will discuss about the comparisons. That means we will analyze each which one is better, and all those things, all the stuff we will discuss in tomorrow session after completing the mini batch gradient descent optimization technique. Now we will discuss about our lab. It is a simple linear regression model using the batch gradient descent optimizer. And today morning I shared the lab link with you. So see, for all the cases I am taking this numerical example same. Let's consider a sample data set have one input and one output. Number of samples are 4. I forgot to edit it. Is a number of samples are 4. Develop a simple linear regression model with one iteration. So if it is a hand calculation, I am suggesting maybe one iteration, but we are doing the program, so you can choose 100,000 or 10,000 using the batch gradient descent optimizer. Fine. So this is the data set. Now I want to write a code to train simple linear regression model using the batch gradient descent optimizer. So first step is initialization. Step 1, there is the initialization. So import numpy as np, which is used for the matrix operations. Import math as empty to do some mathematical operations like power, like that. And import random, which is used to generate a random number. Later, read the data in the form of the matrix. So np.array. So I am reading this data, so which is given in the problem. 0.2 3.4, 0.2 3.4. Sorry. Some maybe Srinath or Sai Babu asked me to zoom the screen, so I am unable to zoom. View table of contents, no. Anyone can tell how can I zoom? F9, no. Function, no. So is it visible now? Is it okay? Is it visible?
Sir, yes sir.
Endana chapra.
Yes sir.
Visible, sir.
Okay, fine, then fine, okay. So but anyhow I will try to figure out how to zoom, how to make a zoom in Google Colab. For today just try to adjust, otherwise say no font. Okay, fine. So it is a 0.2 3.4, 0.4 3.8, 0.6 4.2 and 0.8 4.6. So just I am reading the data. Next step is I have to initialize the model parameters randomly. M equal to, so you can choose any of range. So but for case I am taking the -1 to 1 and C equal to random -1 to 1. I am randomly generating a value and randomly assigning a value to the model parameters M and C. And you assume the learning rate eta equal to 0.9 and max number of iterations I have considered here is 10,000. So almost all the variables have initialized, and also data set is, I have read the data set. Fine. Later gradient calculation. So maybe don't confuse the program. So finally I am come to the what I discussed here. I am taking the same gradient function what I used for the stochastic gradient descent optimization. So dou f by dou m equal to minus into y minus mx minus c into x, and dou f by dou c equal to minus y minus mx minus c, right? So it will gives the dou f by dou m and dou f by dou c, right? So you can figure it out in the next cell what we are doing. Now here for iter in range of maximum iterations, that means this loop will be run for the maximum number of iterations to the 10,000 times, right? So del m and del c, it is called as a this is the gradient of a loss function with respect to m and gradient of the loss function with respect to c initialized to 0 initially, right? So what I'm saying is I will share the close the notebook, right? So try to remember in the explanation I am asking dou f by dou m equal to minus 1 by ns sigma I equal to ns y minus mx. So observe here. So how I write the dou f by dou m and dou f by dou c, gradient of a loss function with respect to m with respect to c. So it is a summation of y minus mx minus c into x over all samples, right? And finally I have divided with the ns. It is a summation of y minus mx minus c into x over all samples from 1 to ns, later divided by ns, right? So for that I am writing the code, right? So what I am doing here is, so initially I am taking the dou f by dou m and dou f by dou c is equal to 0, gradient of a function with respect to m with respect to c equal to 0. Now I am passing all the samples. For sample in range of total number, this is the length of data colon comma 0, it will reflect the total number of samples available in the data set. So what I am doing, so I am taking the one sample, so m value m value is passing, c value also passing, that is coming from this cell m and c values, and I am taking from the data I am taking the first sample 0th column, that means x value, and first sample first column, that is the y value, that is m and c, x and y. I am passing, so these will give the gradients, minus 1 into y minus mx minus c into x, and minus 1 into y minus mx minus c value will be coming here, del m and del c. Now what I am doing, this del m and del c, so del underscore m equal to del underscore m plus del m, that means what I am doing, I am adding, it is a 0, right? So 0 plus something I am adding. In the second sample 0 plus del m, updated del underscore m plus del m. I hope you understand, right? I am adding the one by one. I am adding the gradients one by one. Right? So finally, this loop will be run for the total number of samples. I am not updating. You have to think here. I am not updating the m and c by sample. Just I am calculating the total error by adding. What next I have to do after adding? I have to divide with 1 by ns, right? I have to multiply with 1 by ns or divide with the ns. ns means total number of samples. That's what I am doing here. So it is a summation divided by ns. That is one. So 1 by ns sigma equal to ns y minus mx minus c into x. That by ns coming from here, the total number of samples. And here also it is the total number of samples. So what I am doing here is, it is the final gradient of a loss function with respect to the modular parameter m, and the final gradient of a loss function with respect to the modular parameter c. This is the dou f by dou c, dou f by dou m finally. Now what you have to do, m equal to m minus eta into del m, that is the dou f by dou m, and c equal to c minus eta into dou f by dou c. Now go to the second iteration. So this loop will be repeated until we are reaching the maximum number of epochs. And finally you have to print the m and c values. Right? So now you can execute this cell. and execute the gradient function and run the iterative algorithm. So how much values you are getting here? M equal to 2 and C equal to 2.99999, that means it is a 3. So M equal to 2 and C equal to 3, so that is the final updated model parameters. Fine, this is for this example. Now we will work on some large data set. So now I want to predict. Now I have the a trained simple linear regression model. I have a trained simple linear regression model. Now I want to predict how we can predict. Just push the input value and you have to predict what will be the output. So for that I have to write this code. It is mx plus c, simple linear regression model. So it is asking what is the value of x. So I want to pass something. So to verify, so I am passing the 0.8. So I am expecting 4.6. So I am passing 0.8. So I am expecting 4.6. So this is the 4.6. This is how we are predicting by using the simple linear regression model. So this is for the very small data set. Later we will work on some large data set. Now we work on large data set. Estimate weight of liquid nitrogen based on its pressure. So pressure is the input variable and you have to estimate the weight of the nitrogen, liquid nitrogen. Using the simple linear regression model, consider the batch gradient descent optimizer. And dataset will be available, from this link. So this book is shared with you. You can practice later. So click here. So pressure and nitrogen gas somewhere. Pressure and weight of the cryogenic flow meters. That is the nitrogen gas, and so you have to download the data in the Excel format. Fine, perfect. Now start the coding. So execute this cell, read the data set and create a data frame and print display top 5 entries in the data frame. Why it is showing error? Anyone? Why it is showing error?
File not uploaded, sir.
Yes. So because your data file will be available in your computer, in my computer, but I am working in the Google Colab environment. So you have to push your data into the Google Colab environment. So click on this folder and upload it. And go to downloads. Upload. Fine. Now run it. Still getting error, right? Why? Still I am getting error even though I uploaded. So that
File name, sir.
So that is because of the file name. So you have to give the same file name which is available in your environment. So it is a SLR08. Now you can execute. Fine, it will be the top 5 entries of your data set. What we are doing next? Here we are doing the normalization. It is called normalization. So normalization will be, so it is this normalization we are trying to scale down the values between 0 to 1. We are scaled down the values between the 0 to 1 by using the formula x minus x min divided by x max minus x min. X means the value from the data frame, each value from the data frame. What it is doing is 75.1 minus mean of all these first column, sorry, minimum in the first column. First column is, don't think that it is the 5 entries. So total entries in the complete data set, min value to taken divided by max value minus min value. Then it will scale down the each value between 0 to 1. So you have to normalize the data. So this normalization I am doing here is to avoid the nan error. In Python you will get the not a number error if you got the large, if your during the algorithm process, if you get a very large number, it will throw a NaN error, then not a number error. So to avoid that one, I am scaled down the data. Second is, if you consider the multiple input features, yesterday I explained actually, I want to repeat again because I was hurry in the yesterday. So yesterday, if there are the multiple features, if the multiple features, search space is different. Search space is different. For example, you have an application that whether bank can grant a loan or grant a credit card to the person or not. So it will take some features. Let us assume they consider some features like employment type and date of birth, like that. So I am taking the two of those features, like maybe a sex and also maybe a salary. If the sex is, there are only two, male or female. So we will assign a number 0 and 1, male or female 0 and 1. So in that column you have the only 0 and 1, 0 and 1 values, but a salary in terms of the thousands. If you use the data as it is, then your model will be highly biased to the large values, or it may throw the nan number. So in that case we are using, so in such type of scenarios, so we are using the normalization. So this process of normalization we are called in the Python is called min-max scalar. I am writing a code separately, but you can use a method called min-max scalar in Python. It will scale down your data between 0 and 1 using the same process, but that will happen in the backend. You can call the only min-max scalar as a method. So now I have scaled down the data. Next. Now I am taking a train test split library from the scikit-learn package. So what is the purpose of this train test split is, this method or this library will help you. This method will help you to split the data, to split the complete data into training dataset and testing dataset based on the variable you are passing. Randomly it will develop the training dataset and testing dataset. So train test split, and you have to pass what is the input and what is the output, and test size I am taking the 0.1. That means suppose in your dataset, suppose if you have 100 samples, 10 samples will go to the testing and remaining 90 samples goes to the training. A random state equal to none. That means your goal is not to take top 90 entries for the training and bottom 10 entries for the testing. You have to pick 90 randomly from the 100 samples, and remaining you have to give for the testing. So you have to do it randomly, right? Why you are doing the randomly for the dataset? It is simple. Simple means, suppose as we are most of the participants are the academicians. Suppose a subject have 5 units. And you train the student for the top 3 units, and you are conducting a test on the last 2 units. Is it fine? Is it right way? Say it's not right? Because you are training on some other concepts and you are making the test on the other concepts. So then what we have to do is, that's why we have to do a random. So you have to take some concepts from different scenarios, and later you have to test it. Right? So to avoid that one, we are using the random pickup from available data points as a training and testing. So that is happened by using the train test split method. So here it will throw 4 values. One is the x train, that is the input for the training, x test input for the testing, y train output for the training, y test, that is the output for the test. So it will come out in the form of the data frame. Why it is the data frame? Because we are passing the data frame inputs. Fine. Next, you have to, now our method follows regular batch gradient optimization will follows like this. Import numpy as npy, numpy package as np, and math package as empty and random, and initialize the random m and random c values, and set eta equal to 0.9 and maximum iteration is equal to 10,000. And this is your gradient function. This is your gradient function. Now, so everything similar to the what the right here, what we are writing here in the small data set కన్సిడర్ చేసుకున్నప్పుడు మనం యూజ్ చేసిన సేమ్ కోడ్ యూజ్ చేస్తున్నాం, సేమ్ కోడ్ అగైన్, బట్ ఓన్లీ చేంజ్ ఈస్ హియర్ వీఆర్ వర్కింగ్ ఆన్ ద డేటా ఫ్రేమ్స్. We are reading the data from the Excel in the form of the data frame. Then you are giving the x value and y value in this fashion. You have to use the dot iloc because x train is in the data frame and y train in the data frame. If you want to lock a value from the given data frame, you have to use the dot iloc, and sample means first sample, second sample, third sample. That means from each sample you have to pick x and y separately, and you have to pass x and y to the gradient function. Later we have to sum it, and later we have to divide it by ns, that is the total number of samples. That will give the dou f by dou m value. Once you get the dou f by dou m and dou f by dou c, you have to update the m and c parameters, m equal to m minus eta into something like this, right? That's it, right? So I will, okay, up to here it's fine. Now perfect. So suppose if you are executing over, running is over, next we have to go to next cell. So here actually this x train, y train, x test, y test are in the data frame environment. You have to you have to convert into the array format or matrix format by using the np.array. Later what I am doing here is I want to predict the output by using the trained simple linear regression model on the training data set itself. So for that I am calling, so I am taking the each value from the x train and passing that value to the mx plus c. So it will yptr means actual value during that with the training data. So that value I am appending to this matrix. That means this matrix contains predicted values by using the simple linear regression model for each sample in the training data set. Same thing will be valid for the testing also. This is for the training data set and this is for the testing data set. Here I am passing the input from the training data set, here I am passing the input from the testing data set, and update the ypred test matrix which contains the predicted values on the test data set using the simple linear regression model. Later, so this is for calculating the error matrices, to calculate the error matrices. So I am using the import math, and I am from sklearn matrix I am importing the method mean squared error and mean absolute error, and these methods will help us to calculate the mean square error, that is called 1 by ns into sigma equal to ns yia actual value minus yip predicted value whole square. Similarly, it will help to calculate the mean absolute error, that is the 1 by ns sigma equal to ns modulus of yia minus yip. You can write your own code, or you can use these two methods to calculate the error. So MAE equal to mean absolute error pass actual values and predicted value. It will do the rest of things. Similarly, if you want to calculate the mean square error, so mean square error pass the actual value and predicted value, it will give the mean square error. So is RMSE. RMSE means square root of math.sqrc square root of mean square error. Square root of mean square error. It will give the RMSE, MSE and MAE on the training data set. Why on the training data set? Because I am passing the training data information. Now same thing you can do for the testing also. Same thing you can do on the testing also. Same thing you do on the testing also. So y test, y pred test, y test, y predicted test, y test and y predicted test. Right? So these two cells will help you to give the error matrix for the both training data set and testing data set. Fine. Now fine, you are very happy. That means you have a data set and you have a optimization algorithm and you have a simple linear regression model and you have trained it and you are getting the good losses in terms of some 0.00 like that. So very happy. Now if you want to use that model in the real time, let us assume, so this is for the estimation of the weight of a nitrogen gas based on the pressure, right? So now if you give the model as it is to a chemical engineer assistant or whatever maybe who are using, you want to use your lab, your application, is it work as it is like this? You have a model, you have a data, you have a optimizer, you trained it, and you are getting the good matrices values, error values, reasonably good error values. Now you are ready to sell your application or your model to for the real-time application, or you want to give it to a lab technician who are working in a chemical lab, to chemical lab or some other classroom, wherever it may be. Okay, forget about it. So his purpose is he want to measure the weight based on the pressure he has. Okay, now. So now that model will work as it is. It will work సేమ్. మీరు ఈ మోడల్ ఎట్లాగ ఇచ్చేస్తే వాళ్ళకి అది వర్కౌట్ అవుతుందా? వర్కౌట్ అవ్వదు. ఎందుకంటే యూ ట్రైన్ ద మోడల్ ఆన్ ద నార్మలైజ్డ్ డేటా. You train the model on the normalized data. Now if you give the model as it is to him, then what he will do, he give the pressure value, actual pressure value as an input. Maybe actual pressure value will be in the terms of hundreds, but you train the model with the pressure value between 0 to 1, right? So then what you have to do, before feeding the input to your model in the real time application, you have to normalize it, you have to denormalize it. So what I'm doing here is I'm taking the minimum value and maximum value for the pressure, that is the input, for the weight, that is the output. Now that the lab technician have an option to give the pressure value, and you want to estimate what is the weight. Now this model will ask him enter the pressure value of the nitrogen gas. Now he will give the pressure value of the nitrogen gas, what the data he is available, actual data, not normalized data. So he feeds that data only in terms of hundreds, but you can't give the data as it is to the model, because you have to normalize the data, because your model is trained on the normalized data. That's why you have to normalize that one. You have to normalize the input what the candidate is passing here, right? Like the x minus x min divided by x max minus x min, right? Friends, my question is, why I am keeping float of p here? Anyone can tell why I am taking the float of p here? Why p? Why not p? Why I am taking the float of p?
Typecasting.
Yes, it is a typecasting, because the user is we are using the input command here. Once the user enters the data, the variable p will take the data as a string format, as a string. So you have to convert it to the float. So I'm typecasting here. Now it is a normalized pressure value. Now pass the normalized pressure value to your model mx plus c. Now you get the normalized weight value. So if you give the weight as it is to the user, he will be confused definitely, because your weight will be some 0 to 1, but the actual weights based on his experience, he knows that the weights are in between the hundreds. So if you give this model as it is, then he will be confused definitely, because his weight between 0 and 1, he may call you that your model is not working, it is giving the values between 0 to 1, the nitrogen gas weight will not be between the 0 to 1 at any cost. So then what you have to do, you have to denormalize it. So I am doing the denormalization here as W equal to W norm, normalized value, into maximum value, minimum weight value plus minimum weight value. Denormalization. It is the normalization and the denormalization. Now finally you have to give the value W. You have to give the value W. So this is how we are using. So I will run all the cells. So if you want to run all the cells like this, you can do. You can run one cell by cell, cell by cell, or you can do another way, like from here I want to run, right? I want to run from here, from this cell I want to run. Then go to runtime. Run before means before cells will be up to this cell, the cells will be executed, but I have to do run selection, run after. Run after means from this selection, remaining all the selections after this cell will be executed. So I am doing the run after. So all the cells will be executed sequentially. Don't think that one by one it is executed. Don't think that all are at a time executed. It is one by one executed. All are executed. Yeah. It is showing some error. Why? Why it showing an error? Anyone can tell? Any observation? Anyone can identify what are the bug here?
You have defined RMS,
RMS.
sir, but in
Yeah.
statement you have used MS.
Yes, yes. I forgot to change the variable name here. It is the RMSE, not MSE. So you have to run this cell again. That's enough. Yeah. Now these are the root mean square error values and mean square error value and mean absolute error value. And now on the testing data set, again it is RMSE and here also RMSE. Run it. Right. These are on the testing matrices. And now prediction in the real time. Now it is asking enter the pressure value. So what are the values here generally? I am giving some value. So some I am giving 75.1. I am giving the 75.1. I am giving the 75.1. So it's giving some value. It's a how much it is estimated. So nitrogen gas pressure is 75.1 and estimated value equal to 520, 519. So actual value is 577. That's the difference. Don't expect that we are getting the good accurate with simple linear regression model. At least we are trying somewhere near. We are not getting some negative values, right? Somewhat okay, happy for us. So that's how we are giving. Suppose if you are not converting here, so then your pressure value between the 0 to 1. The actual value is in 570 like that, but your pressure value will give 0 between 0 and 1. So definitely you will confuse, right? So that's why you have to denormalize it before that one. Right? So I hope you understand this lab session also. So you can. I want to close now, and if anyone to leave. I will wait 5 to 10 more minutes for that discussion. So I will close at 8:40. Fine. So I hope you understand. Today we discussed about the how a simple linear regression model will train by using the batch gradient descent optimization, and I explained the step-by-step algorithm and also explained the numerical calculations. Also shown the Python code in the Google Colab. Right. So you can execute this code on your own, and also you can modify it. So because the code is the logic for while writing the code, logic will be changes from the person to the person. So based on my logic level, I have written this code. If you are very good in the programming, and you can try yourself also. Fine. Yeah. Thank you.
Sir.
Tell me.